to finish chapter 6 today and start chapter 7. So let's get down to it. All right, so up to this point, okay, we've been talking about chemical bonds, and we ended last class talking about bond energies and what makes bonds weak or strong or long or short. Okay. So now what we're going to talk about is when you have a molecule, okay, how does charge get distributed? Okay, so how, when the electrons have a choice of more than one place to go, more than one atom to be associated with, what kind of dictates and governs where you find them, okay? And so you've done some of this in lab a couple weeks ago when you generated diagrams like this one right here that show you, again, where electrons are kind of mapped onto the surface of the molecule, okay? So our general color scheme, for those who can see colors, is that red is more negative, which means electrons will spend more time there. Blue is more positive, which means electrons spend less time over there. And then yellow and green are in between. Okay. All right. So we're talking about bond polarity, okay, and what might make an electron spend more time around one atom than another, okay? And we ended last class by making the point that it's all going to come down to the orbital energies and the electron affinity of the atoms involved in the bond, okay? All right, so we have a single number that we use to sort of quantitatively tell us for every element or for most elements what that electron affinity for electrons in a bond is going to be, okay? So we call this electronegativity. We use a capital psi, or yeah, I can't say it right, Greek letter. And this is, again, called electronegativity. It's the ability of an atom in a molecule to draw electrons to itself, okay? So atoms that have higher electronegativity values are going to have more of a pull on the electrons, okay? So the higher the Xi value, more pull on electrons, okay? So the what we call polarity of a bond is going to be determined by the difference between the two elements involved in the bond, or the two atoms involved in the bond. Okay, so the greater the difference in electronegativity, and this is between two atoms involved in a bond, the more what we call polar the bond is going to be, okay? And when we use the term polar, when we say something is polarized, right, it just means a difference between two sides, okay? So you could say, you know, the political debate in the United States has become very polarized, right? It means like there's a huge difference between people, you know, people's opinions on, you know, the left and people's opinions on the right. Okay, so the more polarized, the bigger the difference between the opinions, okay? When we talk about bonds being polar, okay, what we mean is the two ends of the bond, and the ends being the, you know, the nuclei of the atoms that are involved, okay? When we say that's polar, okay, what we mean is there's a big difference or there is a difference in their affinity for electrons, okay? And when that difference is large, we call the bond polar. If it's small, we call it nonpolar, right? So, you know, if there's not a big difference between things, we wouldn't say it's polarized, okay? All right, so fluorine, again, is the most electronegative element. And again, we've been using fluorine as our reference point in a lot of cases. And this is why, because it's the element that is most to the top and to the right of the periodic table that's not a noble gas, right? So it's small, it has high electron affinity, it has a very high ionization energy, and a great affinity for electrons, okay? So as we move away from fluorine, things become less electronegative, okay? And so these are what the numbers look like, okay? So I don't know who chose to have the top of the scale be 4, but that's what we've got. So the most electronegative is fluorine, and it has an electronegativity value of 4, okay? And everything else has lower electronegativity values, okay? So let's talk about, okay, again, remember that electronegativity is affinity for bonding electrons. All right, so let's talk about periodic trends, because that's what we love to do in this course. You'll notice, is there something, aside from the lanthanides and the actinides, is there another group missing from this table that's up there? What's missing? Yeah, that's right. So, well, we have the lanthanides and the actinides, those transition metals that are down here, are missing. These transition metals are still there, okay? So all the way over on the left, we have lithium. All the way over on the right, we have fluorine. Yeah? Noble gases are missing, okay? And the reason that the noble gases are missing, okay, is noble gases are not assigned electronegativity values because they don't participate in covalent bonds, right? They've got that octet satisfied, they're fine, okay? So, don't make covalent bonds. So not assigned electronegativity values, okay? Now, you may notice that, the alkali metals and the alkali earth metals have electronegativity values assigned to them. They don't really make covalent bonds. They make ionic bonds, right? And so, excuse me. So what we're really talking about is elements that that participate in bonds, right? The noble gases like to stay by themselves. What we're going to find is that the electronegativity values of these metals is so low, okay, that when they interact with some of these halogens, right, or some of those elements with higher electronegativity values, they just give up. They give up their electron, right? And so that's when we get those ionic compounds formed. All right, so let's go to our trends, okay? So going left to right, what's our trend? Are we going high to low or low to high? Low to high, right? All right, how about when we go top to bottom? Yeah. It's as you go from the top to the bottom, it decreases, right? So this is high to low. So again, as doesn't matter whether you're on the left or the right, the things at the bottom of the periodic table have a lower electronegativity than the things directly above them. Okay, so those are our trends. All right, so for those of you who are interested in things biological, and especially those of you who might go on to study organic chemistry, okay, there are certain elements that we keep in our head as being things that are highly electronegative. So when they participate in bonds with other elements, we immediately know that bond is going to be what we call polar. So those are really fluorine, oxygen, nitrogen, and chlorine. Okay? These guys are the most electronegative elements. Okay? And so be suspicious when you see one of those involved in a bond with something that is not one of those elements. Again, you're going to be looking at something that is polarized. Okay? Now, we will talk about things being ionic, covalent, nonpolar, polar. Okay? And we put things in categories like that, but realize that every time we make a chemical bond, it exists kind of somewhere on a continuum. Okay? So there's really no such thing as a pure ionic bond. Okay? Even lithium fluoride has some sharing going on, okay? So we take the least electronegative element, the most, or one of the least electronegative elements, and the most electronegative element. And yes, the fluorine really, takes the electron away, but occasionally, okay, that electron is somewhat close to the lithium atom, okay? So we say that has some covalent character. That's the term we use, okay? But in general, yes, Rana. No, so this is like an extremely polarized bond. So we would call it an ionic bond. So the more polar you get, the closer you get to an ionic bond. But even the most ionic bonds have a tiny bit of sharing going on. Yep. So we'll just say this is an ionic compound. With a big difference between the chi value or the Xi values of lithium and fluorine. Okay. All right, so the larger your electronegativity difference, the more polar your bond is going to be. Okay. So, again, the things that you see over on the right here, we would consider ionic compounds. Okay. And the things that are over on the left here are covalent compounds. Okay. But let's look up the electronegativity of iodine and bromine, and then hydrogen and chlorine, okay? All right. So iodine's 2.5, chlorine's 3.0, 2.5, 3.0. Bromine's 2.8. Oops. 2.8. Oops. Is hydrogen on here? There it is, 2.1. Okay. So the difference between these two, and we're just going to do it so the number comes out to be positive, right? Is for the iodine, the bromine, it's 0.3. And then for the hydrogen and the chlorine, it's, let's see, it's 1.1. Sorry. Sometimes it's hard for me to do basic arithmetic while I'm lecturing. All right. So when we talk about these two compounds, okay, they're both covalent compounds, okay, but the difference between these two is so small, okay, we would call this nonpolar. Okay. And it would have a much more covalent, much more equal sharing nature than our HCl, which is a polar, we would consider a polar covalent compound. And so, yeah. Yeah, it is 0.9. See, I told you I can't do math in front of people. Yep, 0.9. All right. So quite often, the kind of cutoff that people use between calling something a polar bond and a nonpolar bond would be like anything more than a 0.5 difference. Okay, so, but really, again, there are, there's, in terms of, this is percent ionic character, so 100% means, the electron completely spends no time around one of the atoms. So when we said this has some covalent character, again, what it means is that electrons in that bond do spend a little time around lithium. Okay, whereas when we get to the purely covalent compounds, they're shared, but the less ionic you get, okay, the more equally they're shared. Okay, so in the case of our hydrogen chloride, okay, the electrons are shared less equally. Okay, so in this compound, they're more equally shared between the iodine and the bromine atom. Okay. All right. So if we look at our hydrogen chloride that we said is a polar compound, okay, we can look at that in terms of one of these surface representations of the molecule. Okay, and again, blue is positive and red is negative in our color scheming when we use these models. Okay, and so when we look at it this way, okay, it tells us again that electrons spend more time here. Okay. The electrons in the bond. It doesn't mean that they don't spend any time near the hydrogen. All right, so what that means, okay, remember that it's the bonding electrons that we're talking about. Okay, so when these electrons, okay, are spending their more time around here, okay, that leaves this hydrogen, okay, the proton in the hydrogen nucleus, with fewer, with an electron deficiency, which means that it has what we call a partial positive charge, okay? And we use a lowercase delta as the symbol for partial charge. And what do I mean by partial charge? I mean anything less than an integer unit of 1 to, of 1, okay? So if there's a decimal place in your charge on your atom, then that means it's got some partial charge to it, okay? So atoms in a polar bond, okay, are going to have non-zero partial charges, okay? And they'll be negative or positive depending on whether it's the more electronegative element or not, okay? All right, and so, again, the bonding pair of electrons is going to be closer to one nucleus, and whenever we're talking about electrons, we've got to remember they're always moving, okay? So this is going to be on average, okay? All right, so when we look at molecules as chemists, okay, one of the things that we look at closely to understand their chemical behavior is charge distribution, okay? All right, so we're going to get back to our, our vocabulary of polarization, okay? And we're going to talk about dipoles, okay? So a dipole, okay, is something with two ends that are different. Oops. And in chemistry, okay, we can talk about, dipole. We mostly talk about dipoles in terms of charges, okay? But in physics and physical chemistry, we can talk about magnets as well, right? Because magnets have a north and a south pole. All right, so this is going to be, when we're talking about if we're talking about a chemical bond. So these are our atoms, okay? And if this is our bond, if the bond is polar, okay, then we're going to have that difference of charge on either end, okay? So a polar bond has a different sign of the charge at either end of the bond. And it's going to have something that we call a bond dipole, or a dipole moment, okay? And we draw dipole moments, okay, as vectors, okay? So if you study any physics, you'll talk about vectors, and vectors are arrows that we draw that tell us the direction of a force or of some difference, and the length tells us something about the size of that force, and the direction tells us something about what's at either end, okay, and how they're different. So dipole moments, okay, will have a positive end, okay, and we designate that by making the end of the arrow a plus sign, okay, so that's the positive end of the dipole, and the arrow, okay, points to the more negative end. All right, and so that's our dipole moment, okay? The length of the arrow, when we represent dipole moments graphically, the length is going to tell you about the magnitude of the difference. Okay. All right. So we had hydrogen and chlorine. So 2.1 and 3.0, right? So we've got 2.1 and 3.0. Let's talk about a bond between carbon and oxygen. Okay. So let's go carbon bonded to oxygen. So if we go back here. Carbon's 2.5, oxygen's 3.5. So tell me, is the dipole moment in this bond bigger or smaller than that of HCl? What do you think? I heard a very quiet bigger from the back of the room. Was that you, Serrano? Yeah, why do you think it's bigger? You're right. Yeah, so the difference between the electronegativities is bigger. So the dipole moment's bigger, okay? And then the arrow we draw to represent that would be bigger, okay? So if I were drawing, it here, okay, whoops. Yeah. All right, let's draw the dipole moment and put the charges in. Which atom is going to have the partial positive charge? If we look at this one, okay, which one had the partial positive charge? The one with the bigger or the smaller? The one with the smaller. Okay, so our carbon is going to be the partially positively charged atom, and the oxygen is going to be the partially negatively charged atom. The difference is larger than the difference in the hydrogen chloride molecule. Okay, so we'll draw the arrow as longer. Okay? So the more, let's see. So the larger electronegativity is the negatively charged end. Okay. Dipole bigger because, the difference in electronegativities is bigger than in HCl, okay? All right, so again, our arrow, okay, is going to be proportional to the size of the charges, okay? The difference in electronegativity. Can you think of something else when we're talking about electrical charges, okay, that's important? So I'll give you a hint. I'm going to mention Coulomb's law again. So what's the other thing, aside from magnitude of charges, that's important when we're talking about charges interacting with one another? What? But yeah, so bond length, how far they are apart, okay? So realize, again, that distance between the atoms is going to play a role. So if you have, if you have a really big atom, they're going to start out farther apart, and that's going to make things even weaker, okay? So I'm just going to say distance between nuclei also matters. All right, so we can have bond dipoles, okay? And so that's one way of looking at electron distribution, okay? But we also need to think about, when we're thinking about chemical reactivity, okay? So chemical reactivity, whether you have lone pairs or whether you have an unpaired electron or whether your bond is polar or not polar, does affect the kind of reactions that you can participate in. It also has an impact on how you interact with other molecules. Okay, if your molecule acts like it's charged at one side and not charged at the other, or has an opposite charge at the other end, it's going to, when it comes into contact with other molecules, it's going to orient itself, right, so that positively charged ends are attracted to negatively charged ends of other molecules, things like that. So two other things that we take into consideration in terms of electron distribution in molecules are formal charge, okay, and oxidation number. Okay, so we're going to talk about formal charge, okay, and so for formal charge, it's going to assume that your electrons are shared evenly. Okay, so we talked about what actually happens with bonding electrons, right? Sometimes one electron hogs them more than the other. Okay, when we calculate formal charges, okay, these are not going to be super accurate in terms of representing what the exact charge on the molecule would be, or on that atom would be. Okay, but it's going to help us make some decisions in certain cases. Okay, so formal charge assumes your electrons are shared equally, and it assigns one bonding electron to each atom. Now, in the case of for example, the bond between the chlorine and the oxygen, okay, when we calculate a formal charge, oxygen's going to get one of those electrons and chlorine will get the other, okay? So how do we calculate formal charge? Okay, it's going to, so our formal charge is going to be your group number, which gives your number of valence electrons. So we get that from your group number, 1A, 2A, 3A, okay. Minus, it's expressed as 1/2 of the bonding electrons. But you can also think of this as, you know, the number of bonds to that atom, okay? So let's do this for the chlorine and for the oxygen right there. So for chlorine, okay, its formal charge is going to be, chlorine is in group 7, okay? So that's its valence electrons, okay? And when we look at it in this particular example, right, the chlorine is bonded to 4 things, so there are 4 bonds. That means 8 bonding electrons. Half of that is 4, okay, so 1/2 times 8, that's 4, 7 minus 4. So the formal charge on the chlorine is +3. Okay. So now let's look at the oxygen, okay? So the formal charge for the oxygen is in group 6. So we've got 6 valence electrons. And this particular oxygen is involved in one bond, okay? So 1/2 times the 2 electrons in that bond, so that's 6 minus 1, okay? And so that's +5, okay? All right. Oops, I forgot to include the lone pairs. I'm like, that's not the right formal charge on here. Sorry. We have to subtract the number of lone pair electrons. There we go. Now we can correct our oxygen. Okay. Minus our lone pairs. So this oxygen has 6 lone pair electrons. All right. So that's going to be 6 minus 1 minus 6. So that's 5 minus 6, so that comes out to be a -1, okay? All right. So what you'll find when you calculate formal charges, okay, is if you calculate the formal charge on every atom in your molecule, okay, those are going to add up to the charge on the molecule, okay? So add formal charges on each atom. That should equal the charge on the molecule, and we'll just test that. And that's how I immediately knew that I had forgotten the lone pairs in the formal charge calculation, because I knew that the oxygen had to be negative, okay? So let's look at it. Okay, we don't have to calculate the other oxygens, so I'm going to just put the formal charges here. So each oxygen has a formal charge of -1. Our chlorine has a formal charge of +3. So we've got +3 minus, we've got 4 oxygens times -1. Okay. So that's +3, sorry, plus our -4. So the sum of our formal charges is -1. And if we look at the molecule, okay, it's a species with a -1 charge, okay? So adding up those formal charges gives you the formal charge, gives you the charge on the molecule itself, okay? All right, so this gives you a much better view of the formula for calculating formal charge, okay? And we can summarize, lone pair and bonding electrons by calling them the quote-unquote assigned electrons, okay? So let's do the formal charges on our sulfur dioxide there. Okay, so this is your Lewis structure. And if we look at the figure on the right, okay, this is showing you the assigned electrons. Okay, right? I've got my lone pair here, okay? And then I've got 1 electron per bond. 1, 2, 3, okay? So if I do my formal charge for sulfur, it's going to be sulfur is in group 6, so that's my valence electrons, my group number, okay? And I'm going to subtract all of my assigned electrons. So I've got 1, 2, 3, 4, 5. So my formal charge on my sulfur is going to be +1, okay? Now let's do the oxygen on the left, and then we'll do the oxygen on the right. And they're not going to be the same because one is involved in a double bond, the other's involved in a single bond, right? Okay, so the one on the left, oxygen also in group 6, and it has 6 assigned electrons, right? If we count these, 1, 2, 3, 4, 5, 6. So the formal charge on that is 0. Okay. Now let's do the one on the right. It's in group 6, but we have this extra electron there that's been assigned to that atom, so that's 7. So that comes out to be -1, okay? Now, we can test what I told you on the previous slide. So these should all add up to the charge on the molecule. So we add the formal charges, and they add up to 0. The charge on the molecule is 0, okay? So that relationship holds, okay? So matches the charge on the molecule. All right. So we'll do one last example with and we'll calculate the formal charge on the nitrogen, okay? So there's the structure, and let's draw just the assigned electrons for nitrogen. So we've got our nitrogen, and it's got 1 for each bond. 1, 2, 3, 4. 1, 2, 3, 4. Okay? Yeah?
Just real quick, on the last one, how can you tell that the Lewis structure for SO2 is the charge is 0? You said you can check it?
Because the Lewis structure is shown and there's no plus or minus sign in it, right? So if it has a charge, the Lewis structure will have plus, +1, -2, whatever it is. Yeah. So if there's a charge there, you will see it. Okay. All right. So in this case, we've got nitrogen. Nitrogen is in group 5. Okay. So our formal charge on the nitrogen is going to be equal to 5 minus our assigned electrons, which is 1, 2, 3, 4. Okay, so that comes out to be +1. So when calculating formal charges, whatever way is easiest for you, okay, to do is that, you can remember this relationship, or you can take your Lewis structure and just look at it and say, okay, I'm going to count, the electrons that are around that atom, okay, remembering that we're only going to count one of the bonding electrons, okay? And then you're just going to take the group number and subtract the number of assigned electrons. So there's kind of two ways to think about it. All right, so why would we bother calculating formal charges if they're not, if they're not going to give us accurate numbers for what the exact charge on an atom is, okay? And the reason is because sometimes we have those non-equivalent resonance structures, and we have to decide which one is going to be the favored one. Again, if structure and electron distribution is going to help us understand and predict chemical behavior, reactivity, physical properties, okay, then we have to be able to make decisions about which Lewis structure is going to be sort of the best representation of how the molecule exists most of the time, okay? And one of the ways we do that is how do we decide which resonance structure is going to be favored, which one isn't, is we calculate formal charge, okay? So if we look, so the things that make for the more favored structure, okay, are these, follow these two rules, okay? So these are going to tell you, come on. So this is which structure is favored. And remember, favored means, lower energy. The laws of the universe mean the molecule is going to exist more in that state than the other ones, okay? Even though anytime you have resonance, you can get all those structures exist, okay? All right, so let's look at carbon dioxide. So carbon dioxide, we can draw three non-equivalent, okay, resonance structures, okay? So we have three structures, okay? Are any of these structures equivalent to one another? So the one all the way on the left and the one all the way on the right are what we would call equivalent, because they're essentially the same thing because there's symmetry. If you flipped the molecule upside down, you wouldn't be able to distinguish them, okay? But they are not the same as the one in the middle, okay? So we have to make a decision. So we calculate the formal charges, and that's what's shown here. And so a arrangement of electrons, okay, because that's what our Lewis structures are, is going to be more favored if it avoids if it's possible to avoid separation of charge. Okay, the system is going to exist more in that state. Okay, so that's thing number one. Okay, so our example of carbon dioxide, okay, tells us that. So this one is going to be the most stable, most favored structure. Okay, so that's how carbon dioxide exists. So now let's look at this anion that's shown on the bottom, the OCN. Okay, so this is a molecule that happens to have the same number of electrons as carbon dioxide. Okay, so everything shown on every molecule shown on this slide has the same number of electrons, but we've got different atoms. Okay, so the nuclei are different, same number of electrons. So now if we look at it, okay, and we're trying to decide which one is the most favored, okay, we're going to say, nope, it's not this one because it has the biggest separation of charge. Not this. Too much separation of charge. Okay, and then when we look at the ones on the right, okay, both of the ones on the right have two atoms that have 0 formal charges and one that has a -1. So how do we choose? Well, we have to use rule number 2, okay, where the negative charge is going to go to the more electronegative atom. It makes sense. That atom has the greatest electron affinity, okay? So which one is that? So we've got a nitrogen, okay, and we've got a carbon. And the nitrogen is the one that has a higher electronegativity, okay? It's more to the right. It's got a greater electron affinity. It's got more protons in the nucleus, right? So electrons are going to be more attracted to that, okay? So this one is going to be our favored structure, okay? Because the charge is on the more electronegative atom. And again, when we're trying to decide between non-equivalent Lewis structures, what we're really saying is which one best represents the reality of the physical world. And the reality of the physical world is that a nitrogen atom has more protons in its nucleus, and it has a higher affinity for electrons than a carbon atom. So if the electrons have a choice, okay, they're going to go and spend more time near the nitrogen. Okay? All right. So that's how we use formal charge. But again, remember, if we were to do all the mathematics of quantum mechanics, what we would have is we would have partial charges. Okay. So formal charge is it comes close to actual value, but sometimes it doesn't get the sign right. And that's the formal charge is what we call the covalent limit. And oxidation number is what we use when we're dealing with metals more and ionic compounds. So we would call this sort of the ionic limit, okay? So it's going to assume that the electrons are taken by the more electronegative atom, okay? So what happens is oxidation numbers will get the sign right, but the numbers are too big, and atoms actually have partial charges. So the point of this is both of these, and we'll talk later about calculating oxidation numbers when we talk about redox reactions, but both of these are, let's say, wrong in the details. Actual atoms, because both of them give you like an integer number, okay? Actual atoms have what we call partial charges. All right, and so when we look at those two atoms those two molecules that were on the previous slide, this is what reality is, okay? Or close to, right? So instead of the nitrogen being -1, okay, it's -0.62. And instead of the carbon and the oxygen actually being 0, okay, one is a little bit positive, and, oops, is that the, yeah, that is. And, one is negative, but smaller negative than the nitrogen, okay? So, all right, so what we're going to do in class on Monday is review some of the stuff that you did in the lab on molecular structure. So we're going to be talking about how we take the information in Lewis structures and decide what the shape of a molecule actually is, okay? And we're mostly going to be just doing a bunch of examples of that and talking a little bit about bonding theory. So just a heads up for chapter 7, we're not going to cover the section on molecular orbital theory. Okay, so there will be no homework on that section, and we're not going to cover it in class. So just a heads up for that. And so chapter 7 we're going to cover rather quickly. Okay, all right. Have a great weekend, everybody.